Hi, I'm Todd Warszawski, and I'm going to be talking about the Legion programming model, along with Wonchan and Karthik. And then also from the Legion team here is Elliott, and Jihao is right over there, right there. Yeah. And I'm currently a student at Stanford working with Alex Aiken, along with Wonchan and Jihao, and then Elliott is over at Slack, and Karthik's a postdoc in our group. Okay, so I want to start off by motivating a little bit why you should use Legion and what the problems are that we're trying to solve. And one of the biggest reasons to use Legion is performance. And so this is an example of the S3D combustion simulation run on the Titan supercomputer, comparing a Legion implementation to a MPI OpenACC implementation. And you can see that at low node counts, Legion is about 2 times better. And at high node counts, this is for weak scaling, Legion's doing about 3 times better. But performance isn't the only reason why you might want to use Legion. We also care about the ease of use when trying to write high-performance codes. So this is going to be a very similar simulation. It's still S3D with the PRF mechanism. And in this case, there isn't an OpenACC version we can compare against, so we're comparing against an MPI Fortran version. And on low node counts here, we're doing about 3 times better. And at high node counts, it's about 7 times better. But a more interesting thing with this computation was that halfway through, we were forced to switch machines. And after only a few hours of performance tuning on a new machine, we're able to get similar performance. And in this case, on Pisdane, we're about 4 times better at both low and high node counts. So what makes writing this performant code across different machines so difficult? The answer is heterogeneity. So if we were to look at Titan, which is currently number 5 on the top 500 list, we see that it has 16 CPUs and 448 GPU cores, and it has system memory for the CPUs and dedicated memory for the GPUs, and shared zero-copy memory between them. And so just programming this one node can be pretty complicated. A programmer has to decide where tasks will run, where to place their data, how to handle data movement. And then on top of that, there's about 20,000 of these nodes on Titan with a high bandwidth interconnect between them. And programming a machine like this quickly gets very complicated. But the problem is actually even a little worse than that. There's, in this ecosystem, what we like to think of as heterogeneous heterogeneity. So this is, again, this is the Titan supercomputer, but it's soon to be replaced by Summit, which has this different architecture with many CPU or GPUs on the same node, and in this case, the latency between them isn't actually even uniform. And in general, a lot of the new machines coming out have very different architectures, and we'd like to be able to get good performance on many of these machines with relatively little effort. Get through this. Right, so this motivates the 3 main goals of the Legion programming system. So first is that we'd like to be able to give good performance. But second, we'd like to give what we call performance portability, meaning that it's easy to get similar performance across different machines and different generations of machines. And lastly, we'd like to give good programmability, meaning it's relatively easy to get this performance. And the way we're planning to do this is we give sequential semantics, meaning that you write your code as if it's going to execute in serial, but you actually get a parallel execution. This makes it easier to reason about. And so Wonchan is going to go more in depth about how the programming system actually works. Just to give you a bit of an introduction, we accomplish this via a task-based programming model. So this is an example program written in Regent, which is a language that sits on top of Legion. And tasks here are the main units of computation. So you can see that you have task foo, which is going to read and write all 3 of its arguments. And there's also a task bar, which only reads its first argument and only writes its second. And then as this program executes, or as task foo executes, the Legion runtime is going to build up a dependency graph of the tasks. So it starts with the first bar task, which has no dependencies. And then it would go on to the second task, which depends on the first, and the third, which depends on the first but not the second, and lastly the fourth, which depends on the other 3. And then it would realize that it can execute the second and third calls to bar in parallel, and it would, you'd get a parallel execution of those two tasks. So the next question you might have is, is this system really necessary? Can we get good performance today? And the answer is yes, we can, but at great cost. And so this is a task graph of one time step of one node, or on one node of just a mini app. And this computation quickly gets very complicated. And so the translation of the three motivating questions are, to get good performance is how will we schedule this graph? And to get performance portability is how will we reschedule this graph every time we want to move machines? And programmability amounts to who's responsible for generating this graph. And today, this is all the programmer's responsibility. Even if you're writing in something like MPI where you're not explicitly constructing a task graph like this, you essentially have to have this data model in mind as you do the computation and the data movement. And we would like to make this the runtime system's responsibility. So just to summarize why you might want to use Legion, it gives you easy access to GPUs and control of a data placement for programming heterogeneous hardware. The tasks are all very execute asynchronous, and the runtime is able to hide communication with useful computation, and Legion is able to give you good performance portability when moving across machines. And now I'm going to hand it over to Wonchan, who's going to tell you more about the actual programming model.
Thanks, Todd. So from now on, I'm going to talk about the Legion programming model. So in the Legion programming model, programs consist of tasks. And a task is a unit of scheduling and execution. So task is just a function that can run asynchronously and run in parallel with other functions. And tasks can take regions as arguments, and you can think of region as a multi-dimensional array. So each entry in a region is indexed with a multi-dimensional point, and each entry in a region is associated with multiple fields. And tasks should declare how they use their regions, or they declare the permissions on regions. For example, in this task, we pass two regions X and Y, and this task requests read privilege on region X and Y and write privilege on region Y. So here's an example of a task. So this XP task is taking two vectors, X and Y, and a constant value A, and computing A times X plus Y, which is a very simple task. And you can see that the region X and Y are actually taking the same index space IS, which basically says that two vectors should be of the same length. And in the following line, the task is declaring permissions on the regions. And inside the task is iterating over each point in the index space and compute the actual A times X plus Y. And just like functions can call other functions, tasks can call other subtasks. And tasks that are launched from the same task are executed as if they were running sequentially, one at a time. But internally, the runtime system will find the interference between tasks to parallelize them. So this is an example that you saw in the Todd slide. And the runtime system first will figure out that there's a dependency or interference between the first and the second bar task because they're using the same region X, and the first one is writing to the region X. And for the same reason, the third bar task interferes with the first one. And the last one actually interferes with the second and the third one. And based on this information, the runtime system will build a task graph and extract the parallelism. And tasks can declare three kinds of permissions. One is read permission, which basically says the task can read from the region. And the second kind of permission is a write permission, which says the task can write to the region. And there's a third kind of permission called reduction permission, which basically says that the task is doing the update only through an associative and commutative operator. And one nice property with reduction permission is that the reduction task can actually run in parallel. So once the runtime takes a stream of tasks, it analyzes dependencies between tasks and builds a task graph like this. And once you build a task graph, it's relatively straightforward to extract parallelism just by looking at a set of tasks that are mutually unreachable in this graph. So Legion applications is executed in 3 wavefront. So there's first wavefront that is running ahead of an application, finding as many tasks as possible, and building a task graph. And there's a second wavefront that is following the first one that actually finds the tasks that are ready in the task graphs and actually running those tasks. And there's a third one that is actually following the second one, finding the ones that are already finished, and reclaiming resources for them. And in the Legion programming model, regions can be partitioned into smaller pieces. And partitioning is a primitive operation in the programming model. So we support arbitrary partitioning of a same region. And actually, this is a key source of parallelism. So in order to extract the parallelism from application, you first need to partition your region into smaller pieces, and you launch a task on each piece. Because this is important operator, partitioning is built into the Legion runtime system and also the language implementation region. So we provide a rich set of partitioning mechanisms from which you can implement your own partitioning strategy. So here's an example of partitioning. So let's say you have a graph like this. That means you will need to have 2 regions, one for a set of nodes and another for a set of edges. And let's say you want to partition this graph into 3 subgraphs. Okay? Then at the first level, we first make a partition between private nodes and shared nodes. So the private nodes are the ones that are connected only within a subgraph, and the shared nodes are the ones that can be connected to other subgraphs. This is to expose the communication pattern to the runtime system. And once you have the first level partition like this, you can individually make a second level partition. So you can partition private nodes into 3 subsets. And for the shared node, you can actually have 2 kinds of partition. One for the shared node of your own subgraph, and another for the ones that are from other subgraphs. And in a similar fashion, you can partition a set of region of edges like this. Okay? So in the Legion programming model, an application is just a sequence of task launches. So it generates a stream of tasks and give it to the runtime, and the runtime system will basically analyze them to find an interference between tasks. And whenever 2 tasks are working on the same data and one of them can update it, then there's an interference. Otherwise, there's no interference, which means you can run them in parallel. And the reason why we do this is to guarantee the sequential semantics of a program. So the program written in the Legion programming model will execute as if it were executed sequentially. And this is a very important property for debugging at scale. And the Legion programming model is implemented as a C++ runtime. So you can use it by writing a C++ application using the C++ Legion API. But we also provide a language implementation called Regent, which is a high-level programming language targeting the Legion runtime. So this is much easier to use, and this provides several static checks to guarantee that your program is actually a valid Legion program. And it also provides several optimizations that the C++ API do not provide, such as vectorization, GPU code generation. So the example program that we show in the slide is actually written in Regent language. So every Legion application has a separate piece of code called mapper. So the Legion application itself doesn't describe where to run the computation. And the mapper will decide the mapping between your application and the actual hardware. So the mapping is a process of assigning resources to Legion tasks. And then conceptually, it assigns a processor to each task and assigns a memory to each region argument. And actually, this mapper is an arbitrary piece of code. It's an imperative program, so you can do anything you want, theoretically. And even if any Legion application should provide a mapper, you don't have to write it from scratch because we are providing a default mapper that does a regional job for typical cases. And the default mapper is not baked into the runtime, but it's just another mapper, which means that if you want to override the default behavior, you can just override some functions in that default mapper. So we provide two kinds of interfaces for mapping. The one is in the C++. So in the C++ implementation, you will implement a set of callbacks, which will be invoked at a particular point of the task lifetime. So this means that you have to understand well about the lifetime of your task. So this can be sometimes very difficult to write a correct mapper even. So we provide a second kind of interface, which is a DSL. So if you write a mapper in this DSL, this will be compiled down to the Legion mapping API. So this is much concise, much easier to use. But currently, this only supports static mappings. So we'll keep adding features to this language. So here's an example of mapping. The application has to select where to run the task and where to put the regions. And for this kind of machine topology, let's say we have 5 tasks, then the mapper can do something like you want to map task T1, T2, T5 on CPUs, and T3 and T4 to GPUs. And for regions, the ones that are accessed by the CPU task should go to DRAM, CPU memory. The ones that are accessed by GPU task should go to frame buffer. And this mapping decision is computed at runtime dynamically. So if you ever want to make a change in the mapping decision, you can actually monitor your execution of your application and adjust your mapping decision at runtime. And the goal of having a separate mapping API is to decouple the performance of application from the correctness of application. This is an important property for the performance portability. So this makes it much easier to port your program from one hardware to another, because you only need to change your mapper, not the application itself.
Yeah, okay. Thanks, Wonchan. So in this portion of the talk, I'll focus on the Legion tools ecosystem and some of the prominent applications that we have developed using Legion. So we provide robust support to ensure both correctness and also to do performance analysis of Legion programs. So for example, on the correctness side, we have a lot of command line knobs that you can use. For example, in the debug mode, we enable a lot of checks that will help you pinpoint to either an application error or a runtime error. It could be one or the both. And then many of you might have debugged sort of distributed executions with sporadic failures. Even before getting to the failure, it's a challenge to get to the failure, right? So we have a freeze-on error where the user can use to stop the application in the case of an assertion failure or a seg fault. And then he can GDB attach to the offending task or process and then debug further from there. And one of the important things in like an asynchronous task execution is sometimes you want to know that your tasks were executed in the order that they were issued. That is, you don't want the runtime to extract the parallelism automatically. So in that case, we have an in-order execution where like the tasks are executed in the order they are issued, like sequential semantics. And the two important tools that we feel are the Legion Spy and the Legion Prof. So the Legion Spy provides a recording of the tasks and the dependencies in the execution. So an output looks like this on the top right of the slide. So you have the boxes which represent the operations, and the edges between the boxes represent dependencies, explicit dependencies. So this can help validate what a user has in mind about the task dependence graph. So you will say like, why is my task not running in parallel? And he'll see like sort of those two tasks are dependent on each other. They have an edge between them. And then he can resolve the permissions in order to resolve sort of the parallelism issue. On the Legion Prof side, so it's a visual profiler sort of the execution. So it helps you track dependencies, timing information about the different tasks. So each processor has a separate timeline, and intervals on each of the timeline will specify different operations. And we also have the ability to track sort of the critical path through these operations. Now you can also do something like, you can also look into the region prof output and then say when a region instance was created, when it was destroyed, and how long does a low-level copy actually took in the execution. Now you'll see an output in the S3D context in a couple of slides, so that's why I haven't shown you a separate output here. So that's about the tool. So we feel we have a good set of both correctness and performance analysis toolkits that help guide the programmer to the actual error or to the actual performance bottleneck. Now, jumping into the application. So S3D is sort of our flagship full-scale large application. This is contrary to how general parallel programming models have been evaluated in the past. They're evaluated against a bunch of mini apps, and you sort of hope that the performance translates to a larger app. And that's not been the case, not just with respect to our programming model, but with many other programming models. So that's why we sort of deep dived into S3D right from the beginning of sort of the Legion programming model introduction. Now back to S3D. S3D is actually a combustion simulation. It is used by the Department of Energy researchers actively in order to sort of study the chemical and physical properties of fuel mixtures in an internal combustion engine. The simulation is basically characterized by the type of reaction that you're trying to do. So for example, there is DME, heptane, or PRF. And on the computational side of this, what you have, if you just don't want to sort of deal with the physics and the chemistry of it, there is a regular Cartesian grid, and there are values at each of these points on the regular Cartesian grid. And these values, each of them is called a species. And based on the reaction that you're simulating, it could be different number of species. For example, heptane has 52. So 52 values at each Cartesian grid point. Now, in reality, in the actual physical experiment or in the actual physical world, there are actually hundreds of such species and then thousands of reactions working on these species. But that is computationally intractable. So that's why the MPI version or the version that is actively researched or our Legion version just uses 52 species. And for heptane, it uses around 238 chemical reactions. So one side of it was the data, which is the Cartesian grid with values at different points. And the second side is actually a computational loop that does a 6-stage, 4th-order RK method. And then inside this loop, the most computationally intensive part is the RHSF function, which is the right-hand side function, that actually does contains these reactions, 238 reactions for heptane, for example. So as you can imagine, having these 238 tasks in mind when you're trying to schedule the whole time step loop is impossible. So it's impossible to do, let me rephrase it. It's impossible to do a good job of scheduling those tasks. And that's where the Legion power sort of comes into play. Legion is automatically extracting the parallelism between these 238 reactions and also the sort of subtasks that these reactions can spawn, and then scheduling it to get you the 3x and 7x performance improvement that Todd mentioned earlier, both for low node counts and high node counts. That is like 8,000 nodes, half the system in Titan. So you can think of it as, if you think of 30 cores, including the GPU per node, you're looking at around 250,000 sort of parallelism in the large count case. There is a reason why there is a dip on the rightmost end. You can see it's sort of significant both in MPI and Legion. That's because we ran this genetic algorithm which remapped the ranks to processors, which the MPID ring gives you. So that both of them have the best possible sort of communication costs between the tasks. And that's why both of the genetic algorithm did not complete within 15-minute time slot that we gave at the beginning to remap the tasks. And that's why, so effectively at 13,000, they are just running without the genetic algorithm mapping. So, important thing to remember is that the Legion runtime automatically extracted the parallelism from these 238 tasks and their dependencies and scheduled them on these nodes in order to get that 7x improvement. There was one more thing that sort of Wonchan pointed out too, which is sort of decoupling correctness from performance. So when I said 7x performance improvement, one aspect of it was extracting parallelism, and second was mapping it to those nodes. And those nodes have both CPU and GPU. So an important point of a design point is how much to put on CPU and how much to put on GPU, and sort of where's the data placed when that happens. So something that we learned while doing S3D was one of the computations, namely the derivatives of the diffusive flux fields. It's sort of a tricky task because it has a significant memory footprint. So because of which, so either you relegate it to sort of the CPU side or the GPU side, and also all its dependent tasks need to work there because there is minimal sort of opportunity for overlap between computation and communication there. So, but the point being, with the mapper API, it is so easy to change these mappings that we actually tried out 150 mapping strategies before settling down on this, which gives 7x improvement. And there is a good sort of distribution of workload between CPU and GPU here. And sort of the 4 cores for Legion runtime were necessary because there are a lot of tasks, as I said. So one of the things about the Legion runtime is it does have an overhead, but the overhead is proportional to the number of tasks and not on the input data size. So you can be working on 1,000,000 points, but if it is 2 tasks, then there's 0 overhead, literally. So what that means is as you go to sort of a larger workload, you don't see the overhead of the Legion runtime, and then you can just use just one core to actually do all the work for the Legion runtime. And then you can use the other cores effectively in order to do the actual computation. The point this figure is here is because the K20 it looks like it is less utilized. And the reason is the 96 cube sort of Cartesian grid that is needed for each species could not be fit on the K20 side because you have like 52, and for each of these species you have like 500 temporary variables, so it is like 52 times 500 times 96 cube and so on. So it quickly scales up, and the GPU did not have enough frame buffer to hold the sort of tasks that needed to be assigned to it. That's why it looks like it's minimally used, but it's because of the limitation of the frame buffer. And I forgot to mention that these graphs, that these two, what you see is the exact output from Legion Prof. So empty space means idle time, and that helps you sort of boil down to the performance bottleneck directly. And that's why it's very useful in our performance analysis of Legion programs. A second sort of interesting application that we'd like to showcase is our work on CNNs. So as most of you might know, that CNNs are actually very effective for image classification, face recognition, game playing, and it keeps growing year over year. So as the applications increase, as the training data sizes increase, so sort of the computational requirements are growing. Now, apart from the model side, now you start thinking on the computational side where you need to introduce more parallelism strategies to make it like sort of feasible, right? So, but many existing strategies can be classified into 2. So either they are data parallelism, wherein the input data set is actually divided into batches and assigned to different compute nodes, and then you let it work there. Or you have model parallelism, where you divide the network parameters into disjoint sets, and then so sort of each compute unit trains a subset. But whatever tools that are out there, they actually apply the same strategy to all layers of the CNN, and that's actually not perfectly necessary because, for example, a densely connected layer with lots of parameters, in order to reduce communication, might prefer model parallelism, whereas like a typical convolutional layer usually might prefer data parallelism. And not only, say, preferring data parallelism at a layer, what you can do is you can go a further level saying that I'm going to sort of partition or create the parallelism based on a particular dimension. So for example, if you're looking at an image classification problem where the data is organized in 4 dimensions, image, height, width, and channel, you don't want to parallelize only in terms of image. That is, slice up the images, get the parallelism out. You want to like try maybe height, maybe the width, maybe the channel. Now, initially, your intuition might say that's not actually fine. But so, for example, the first line there showing around 30 seconds of execution is based on an image-based parallelization strategy. This is from a paper, Simeon and others in 2014. And it's the Conv8 in the VTT16 network. But what we did, so this is actually headed by Jiha. Jiha has done the main work on this. So you can see that if you parallelize by height, you're actually getting better performance. And that might be only for this layer, and for some other layer it could be a different, sort of a different dimension. So that formed the motivation for our work here in the area of CNNs, where we explore sort of other parallelizable dimensions and also allow each layer to be parallelized differently. And that's where we introduced the framework called Deep. It means it's a play on the word deep parallelism, on the words. And it's a framework in Legion to support the development of CNNs. It includes a cost model that sort of estimates the performance of different configurations. And now, since you have a cost model, obviously there is like an exploratory space here where you solve a global search problem in order to identify the optimal parallelization strategy. And without getting into too many details here, so what you can see is we kind of outperform most of the sort of the things on the market, frameworks on the market, for example, PyTorch and TensorFlow. So in fact, for the LXNet, network, we are around 7 times faster than PyTorch and around 4 times faster than TensorFlow. And not only that, so our framework forms like a test bed where you can apply things like OWT, which is the one-weir trick where you can switch between data and model parallelism between different layers. And these are on 16 GPUs, where the batch size is around 512 images. So in summary, what we actually presented to you today is like an exascale-ready programming model where we alleviate the programmer's concerns in terms of sort of scheduling, sort of working out the details for the low-level details of actually mapping. And the programmer just describes the initial structure of the program and then the tasks that operate on that data. And the runtime automatically extracts the parallelism, gives you the guarantee of sequential consistency, and also does the underlying low-level mapping stuff. And we also give you a regent programming language that improves the productivity of this C++ runtime. And sort of on the right, you see our software stack, and that summarizes the things that we presented today. That was all. Thank you.